Okay, I hope we are on the YouTube now. Are there any questions about the previous lecture? Okay, if no, then let's move to today's topic. Today we will not talk about quantum groups at all, but we will, despite of this title, affine quantum groups, but we will talk about affine algebras. This is a classical subject, but actually appeared about around the same time as ordinary quantum groups. But I think that it will be good if I recall something about them, because the subjects are rather huge. One of the first definitions of them is given through loop algebras. And just maybe I should say in the beginning that every algebras which today I'll speak about affine algebras, and all of them will be untwisted. So if you know what is twisted, then we will not have them such algebras. If you don't know, it's even better. And the initial definition is the definition of the loop algebra. So assume that we have simple or semi-simple the algebra G, then we can take this tensor product G times C T inverse. And I will use notations for the element of the space. So standard basis is the elements like x times t in power n, where x is some element of the base of G. And I will shortcut such elements by x with some index n, or x with a n in square brackets if you have, my index will have some other index. So this is a loop algebra, and affine algebra is a certain extension of this algebra. And actually there are two notions. One of them is G hat. I will use this convention is not completely standard. Some people use different conventions. It's not a big deal. So one of the is G hat, where I add some central element K, and another which I denote by G tilde, I add central element K and also some differential D. So this is the definition of the affine algebra as a vector space. And now I have to write down relations of this algebra, and relations has the following form. If I take commutator of some x, n, and y, m, it will equal to commutator x, y, n plus m. This is a commutation relation in loop algebra. So this is a tensor product of the Lie algebra and associative algebra, and I take multiplication on the associative part and commutator on the Lie algebra part, plus n plus a part which corresponds to central extension. And this is the square bracket is some killing form. I will specify normalization a bit later. If the simplest case, the standard convention that H alpha has length 2. Square of length of H alpha is 2. And so if you take commutation of the standard elements here like this, then I get ordinary commutator plus central extension. And if I take commutator with a k, then it will be 0, k is a central element, and d is a differentiation. So as a remark, one can think that D is equal to T dt. In principle, just could be there is something to prove that this is indeed the algebra, that the Jacobi rule is satisfied. It is a straightforward, and I will not even give it as a problem. So just I see. Yes. Okay. Okay, this algebras. When we talk about simple algebras, very natural object is a corresponding description in terms of roots. So let me recall this stuff for in the affine case. So the algebra G has the form as Cartan part plus the direct sum over all roots of this Lie algebra of G alpha, corresponding roots subspaces in G. And this loop algebras, the largest one, G tilde, has a corresponding decomposition. So G tilde is a Cartan part, which I denote by H tilde, plus the sum over roots, which are affine roots. Maybe I could write here F tilde, but I just write A as a superscript, G tilde alpha. What are the subspaces? H tilde and G tilde alpha. H tilde is a Cartan part of the original algebra, where I add a central element and differentiation. If I want to write out this corresponding decomposition of G hat, then instead of H tilde, I will have H hat, and it will be given by this formula. And also for loop group algebra, it also will be similar decomposition, and the same everything. And this affine root system is the following. So this is a set of elements, alpha plus and delta, and where this numbers alpha and n, here is misprint, alpha is a element of the is a root, but okay, maybe too much. This not this could be alpha, it could be root or 0. And n is an integer number. And alpha and n belong to the product of, it can be any pair except the pair of 0, 0. So it is prohibited that both of them, alpha is equal to 0 and integer number 0. It is prohibited to have 0. 0 is not a root, as we have for phi. The corresponding subspaces are the following. So G tilde is alpha plus with the index alpha plus and D is just G alpha times T in power n. And G tilde and delta, where we have 0 alpha, which it will correspond to the Cartan part. So we have a Cartan in the Lie algebra part times T in power n. Any questions? What should be clear now that this indeed we have such equality. So so any element of G tilde is a linear combination of the Cartan part plus this such weight spaces. Okay. 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 No question. No question. Of course, this decomposition is not just decomposition of the vector spaces, but this is decomposition with respect to the adjoint action of the Cartan. So if I take Cartan element So the space G tilde alpha is a weight space for Cartan. What does it mean? It means that, so if I take any element of this Cartan, x plus some number, I don't know, ckk plus cd d, then and act okay, I don't know how to write formula in a good way. Just let me say in words. So if my alpha has a form alpha plus nd, it means that for elements of Cartan which belong to original Cartan, they act by weight alpha. K acts by 0 because this is a joint action, K is central. And D acts by number n. So this element D, okay, let me write it here maybe. Here. So alpha belongs to, is a weight, it is a root, in particular it is a weight, so it belongs to dual space to the Cartan. It is a linear function on the Cartan. And with respect to the decomposition, I can embed H dual to H tilde dual. So these are the elements which vanish on K and D. And also I have element delta, which vanish on H and vanish on K, and delta on D is equal to 1. And in order to write down the full the basis in the dual space, I will have to introduce one more element which I denote by pi 0, which vanish on H and vanish on D, but applied to K is equal to 1. So for the dual space, I have decomposition. This dual space for original algebra plus C delta plus C pi 0. I don't know, maybe just to write down some formula. So we have on the original space, we have Cartan K and D. On the dual space, we have dual Cartan, we have delta, and we have pi 0. So and in the pairing, here we have zeros. And here we have 1, 1, 0, 0, and here we have pairing between H and H bar, H star. You can ask why I use notation pi 0. This is because I plan to use other pi's, pi 1 and so on, pi r, as for the fundamental weights corresponding to original algebra G. So pi 1, pi r, maybe wait, maybe I can write it just now, just now. So pi 1, pi r, fundamental weights. So the elements of the belong to H star, and they are fundamental weights for original algebra. For maybe for phi, for the system. So this means that, okay, I suppose that everybody knows all this. Are there any questions? So this is some sort of long preparation to talk about affine algebras. I introduced them as in this formula. First, we have this formula, then I use this decomposition, and for the later I will use the notation for some weights, fundamental weights, and so on.
Sorry, the fact that delta vanishes on H and K is the definition of delta, yes? A little bit high over there.
Yes, this is the definition of delta.
Okay.
Other questions? Okay, everything is clear. Then let me put a bit more notation. So I remember theta, the highest weight. So the highest weight of adjoint representation. So this is the root of, let me write down, adjoint and let me even write down that this is the root theta. The highest weight of the adjoint representation. So let me draw a picture. In such cases, people usually draw SL3. Okay, so here are roots for SL3. So usually this will be alpha 1 and alpha 2 simple roots. Then the highest weight is theta, which is equal to alpha 1 plus alpha 2. So this is a positive root, suggests there is no roots. If we add to it any of the alphas, it will be normal root. Okay, so this is the highest weight of the adjoint representation. Maybe I reorganize my slides. Okay. Then the corresponding element, say x theta, satisfy the following property, that if I apply adjoint x minus alpha e I to x theta in the power theta alpha I check plus 1, it equal to 0. So in this picture which I draw, it means that if I apply which maybe one more color, if I apply this way x minus alpha 1 twice, I get I obtain not root, so it vanishes the adjoint representation. This is a property this is a property of any affine dimensional representation. So if you have highest weight vector and apply generators of some SL2 subalgebra, then this element should generate the fine dimensional representation of SL2 and in such representation, we have singular vectors. This have Punisher single vector, and this is condition. I use here notations x with an index of root instead of maybe more standard notations e and f, e, I, fi, because I plan to use e and f for in a minute for closed, but a bit different meaning. So I keep this notation. Are there any questions about this formula? Maybe I add what I maybe draw the formula in blue color, some sort of. It's not blue. This is I don't know, teal color, and add what I said in words. And in words I said that general affine dimensional representations. If we have v lambda in v lambda highest weight vector, then x minus theta in some power alpha I check lambda plus 1. For simplest case, this is just scalar product of alpha I and lambda equal to 0. Okay, this is my explanation. Okay, and the reason why I introduce such element is the following. So I will have I can introduce another set of generators in the affine Lie algebra. Namely, let me denote E1 for I from the set 1 to R. I denote EI to be X alpha I. Maybe I should recall that alpha 1, alpha R, the set is pi, and this is a set of simple roots. I said recall because I hope that I use this notation in first lecture, but who knows, so better to recall. So Fi is X minus alpha I, then 0. Then E0 is X minus theta 1, and F0 is X theta minus 1. H I is H alpha I0, H0 is K minus H theta. And then this set of generators, EI, FI, E0, F0, they satisfy properties of the Chevalier generators of the Katz-Moody group. So these are. maybe not, but say not group, Kac-Moody Lie algebra. What does it mean? It means that we have the following relations. Let me use the colorful formulas. So we have EI Fj is delta Hj Hi, Hij is Aij J, where this A is a Cartan matrix. I will say now affine Cartan matrix. Minus Aij Fj and plus shear relations. Okay, let me write down them. So if I apply adjoint I in power minus Aj plus 1 to Ej, I get 0. And the same for F. So these are shear relations. I. So should be I somewhere, yes. Should be I think here. And I should set what is Aij. So Aij. So in order to define Aij, you have to just add one more simple, affine simple root. So I denote because the simple root alpha 0 is delta minus theta. And A0j is a scalar product of two scalar product delta minus theta alpha j over scalar product delta minus theta is delta is orthogonal to all roots of the original algebra. So delta disappeared here, and we have minus 2 scalar product of theta alpha j. And similar for AG0 differs just by the denominator, which will be the scalar product of alpha j with itself. So these are standard presentation of the Kac-Moody algebra. The Kac-Moody algebra is presented in terms of Chevalier generators. We have E's, we have F's, and we also have H's. Let me show this on the picture. So first example is the algebra SL2. It has it's three-dimensional. It has standard generators E, H, and F. But because I used E and F for generators of the Chevalier generators for the affine algebra, so I used X plus instead of E, X minus instead of F, and X0 instead of H. The affine algebra G tilde can be symbolically drawn in these three columns. So for example, the last column is the elements of the form x plus time t in some power n. I denote them with square bracket, so we have just original x plus 1, x plus 2, x plus times t cubed, and here x plus times t inverse, and so on. Similarly, we define the left column. So x minus times t, and so on. And middle column is this x0 times similar powers of t. This is a regional representation of the affine Lie algebra as a loop algebra. Here I draw big circle. It means that in the Cartan part, we have also added K and D. They all belong here. You can see that in the axis, so this x corresponds to regional H0 gradient, Cartan gradient on the SL2, and this vertical directions correspond to this operator D, its gradient. Okay, and now what are my Chevalier generators? So we have only one simple root. So if we compare with this, we have R equal to 1. So we have to pick E1 and F1, which correspond to X alpha 1, and so X alpha and X minus alpha. So E1 is this element, X plus 0, F1 is this element. And E0, theta is again is the same as alpha because we have only one simple root. And by my definition, E0 is x minus theta 1 times t. So here it is here. And F0 is here. I don't know, it will be. So we have this for such decomposition of the algebra. So we have subalgebra, which is we have a decomposition also in two subalgebras. So we have upper half, lower half, and Cartan part. So we have a decomposition. G tilde is B minus tilde plus, no, B minus. Where this n plus tilde is the sum of G tilde alpha for alpha positive affine root, and positive affine roots are, okay, let me find some place. And this positive affine roots phi A plus is a union of it is the elements of the form alpha plus and delta, where either n is greater than 0 or n is equal to 0 and alpha belongs to is a positive root. No. And phi minus is opposite. So we have either negative n or alpha is negative root. So in this case, this is phi plus. Such roots belong to phi plus. Such roots belongs to phi minus. Are there any questions? When I said in words that we have this Kac-Moody algebra, then I somehow assume that we should have such sort of decomposition. I mean, not assumed, prove. If I prove that this Kac-Moody algebra, then I prove that we have such sort of decomposition, triangular decomposition. This subalgebra generated by E's, so this subalgebra generated by F's. Maybe I should write this. This is generated by I said what proof, so there is something to prove here, namely these relations. These relations are quadratic, so they just follows from the definition from the original algebra. And non-trivial part is the part which corresponds to Serre relations. Serre relations which do not involve zeroth root, they are straightforward. They just because we have them just for simple Lie algebra, and those which involves additional zeroth root, they follows from this property, from the fact that x theta is the highest weight, is a highest root. So it is the highest weight of the joint representation, so it satisfies this property. Maybe I should add that we assumed here that theta is equal to 2. So we pick such normalization. Maybe this doesn't matter, but for me it will. Okay. If no question, maybe I should ask audience who knows what will be the Cartan matrix for the affine SL2. What is this? Will be the size?
2 minus 2 minus 2, 2.
And how do you know this? Just know, or maybe you can compute it from the definition which we get.
Well, if we compute, it follows from the Dynkin diagram for affine SLN, but for SL2, -1 and -1, they add up to -2 on the offsides.
Okay, I prefer to say that we have this formula. So in this case, this additional, we have to compute only number 0, 1, and here theta is the alpha, and this is also alpha. So on the numerator we have -2 alpha alpha, and in the denominator we again have alpha alpha. So alpha A01 is -2. So let me draw that Cartan matrix is 2, 2, -2. Note that we get not simply laced Lie algebra, but all roots have the same length, so we'll at least we will not have problems with different Qs and stuff like that. Okay, maybe I want to spend some time also for the next example, SL3. Okay, so we have G is equal to SL3. This is a picture for G tilde as before. You see SL3 is, I draw SL3 as a hexagon with a bolded origin, because in the Cartan we have, on the SL3 we have two-dimensional space. here even more. This zeros level of the loop algebra. So here we have Cartan and also we have K and D, two additional generators. This is Cartan. This will correspond to our generator X alpha 1. Like this. And this will be X alpha 2, X minus alpha 1, X minus alpha 2. And since I draw them in the loop group, so this zeros level, I draw 0 everywhere. This will be the first level, so X alpha 1, 1. This is a minus 1. X alpha 1. And so on. And now I want to relate these generators to Chevalier generator, which I at least promised you before. Maybe I need more space. I move this levels a bit lower. Okay, who can help me? Where to write down Chevalier generators? So I want to draw similar as I wrote here. So here I used some another blue color. I wrote generators E0, E1, E1 is 0, F1 is 0. Using my definition, I said EI correspond to simple roots and E0 correspond to highest root. So what to do in this picture? Where will be E0, E1, and so on. Okay. Maybe somebody knows, but just I mean to afraid to answer, don't want to spoil or my question is not clear. Okay, please say something. Do you hear me?
Yes.
Okay, Sasha, do you know where to write Chevalier generators? Who are the Chevalier generators in this case?
Ну, немножко отвлекся. Там SL2 сейчас, да, у нас?
Now SL3, we have SL3.
Тогда у нас в SL3 случае у нас, значит, ну, значит, сейчас у нас есть Картан, надеюсь, понятно. Значит, все Шевале-генераторы из самой SL3, и еще нам нужен один корень, который... Ну, чтобы верхнюю половину сгенерировать, нам нужен еще один корень, который, значит, при... Ну, самый отрицательный, видимо. и умноженный на t.
Okay, so where is in this picture? So these are, so we should take original Chevalier generators. So this is E1, this will be E2, this negative ones, F2, F1 and F2. And so this is on the zeros level, and we should take the most negative one multiplied by t. So the theta is here, so here is x minus theta. And x minus theta 1, and it is equal to my additional generator A0. And correspondingly, F0 will be here. I don't know how to make this more visible. Okay, who can hear me besides Sasha? Who?
I can hear you.
Да, слышно. Еще вы 2 раза F1 написали на картинке.
Oh, thank you. Are there any other mistakes or I don't know questions? Okay, I hope that there are no more questions. That everything. I hope that everything is clear. So what we had up to now, we described that there are two presentations, two ways of thinking about affine algebra. One is in terms of the just loop algebra and this natural definition, and another in terms of the as a Kac-Moody algebra for affine type. Maybe I don't know. Well, maybe will be helpful or not. Let us. Maybe I can ask what will be the A Cartan matrix in this case. Okay, I'll ask and answer myself. So we have on the bottom part, we have Cartan matrix for SL3. And here, again, by using this formula, all roots have length 2, so this part cancels. We have minus scalar product of theta and corresponding alpha. Theta is now alpha 1 plus alpha 2. Alpha 1 plus alpha 2 with alpha 1 is equal to 1, and the same for alpha 2. And since we have minus, so we have minuses here. In particular, you can see that this formula is symmetric with respect to permutation of the simple roots. And this symmetry was not obvious from the original definition. So we have additional automorphisms which do not preserve such homogeneous grading with respect to D, but nevertheless they are automorphisms of the affine algebra. They permute these simple roots E0, E2, and E1. And this is somehow, and in general case, we also have additional automorphisms which will cyclically permute simple roots. Here we have whole group of permutations, but later we'll have just group of the size 2n, cyclic permutation and one symmetry. Okay.
So in the SLN case, the matrix would look like the Cartan matrix of SL n minus 1, and we add like 2 in the angle and minus 1s in the top row and in the left column, something like that, right?
Yes, yes. Mm-hmm. Okay. Since we realized that affine algebra is a Kac-Moody algebra, we can talk about its while group, which I call affine value. So its definition just for any Kac-Moody algebra, just for simple algebra. So this is a group generated by simple reflections, which correspond to simple roots. Now we have r plus 1 simple roots as 0 and so on as r. Subject of relations that each of them is in involution, and they should satisfy braid relation. And these numbers Mij are given by the table. And okay, sorry. Yes. I mean, for those who are interested, we are giving lecture actually of online and offline also. So I share my screen via the projector. But I'm not sure that it is very convenient for people in the audience, but okay, they say that it is at least okay. So everybody is welcome to come to Skoltech and attend the lectures offline. So this is some sort of abstract definition of the group. This group will be not longer finite group. This is infinite group, and how to think about it. And we will use this group when we talk about quantum groups, for example. And of course, while group answers for many questions related to the Kac-Moody algebra, so this group deserves some study. Okay, so how to think about the representation of this group? Usually, such group acts on the Cartan or dual space. So let's first talk about the Cartan, or actually here we have dual. So we have a dual space, which is again, it is a dual space to original Cartan plus C. Okay, this is vector space which is generated by simple roots alpha 1, alpha r, and also two additional elements which we added, delta and pi 0. And in this realization, this group, is generated by simple reflection. By reflections. As usual, it is sufficient to take reflection with respect to simple roots. So, namely alpha 1 and so on, alpha r, and also alpha 0. I recall that alpha 0 is delta minus theta. Maybe you can ask, what do I mean by reflection? And if we can think that we have scalar product on the space, such that I already used the scalar product many times. And then for any element, we have the corresponding reflection. So S alpha of V is V minus 2. Here, okay, this is standard formula. This here the reflections with respect to simple roots, but I should add that all reflections yes, for not, yes, sorry. Here should be denominator. Thank you. All reflections belong to this group. Now note that this element delta is invariant under the action of this group, because delta is orthogonal to all these roots. Okay. Let me write this in this way. So we have generators alpha 1, alpha r, delta, and pi 0. Alpha 1, alpha r, delta, and pi 0. And the scalar products here are just original Cartan matrix. In the simplest case, assume that we don't have such denominators. Delta is orthogonal to all this alpha 0, alpha r, and I don't time like pi 0 is also orthogonal to all of them, and they pi 0 and delta have scalar product 1. So we have such form which is non-degenerate, but not positive. So matrix A is usually positive, positively, how it's called, positively definite, положительно определенная. But since we have this two-dimensional space with such signature 1 minus 1, so in the whole space we have this scalar product is not positively definite. And we have hence the vector delta is orthogonal to all alpha i's. So hence delta is invariant. Hence delta is invariant, and therefore we can consider not R plus 2-dimensional representation of the affine value group, but the representation of the less dimension. There are actually two ways to take this. One is the following. So we can consider the space H plus, so we can consider take R plus 1 dimensional reps of WA. There are two ways which are actually dual to each other, as we will see. So one way is to take the space generated by alpha 1, alpha r, and also delta. And this is the same as take the space generated by alpha 1, alpha 0. And this is quite natural. So we have roots. So why take anything else? Why to take this only pi 0? You can think that, okay, so this is a space, the space is dual to the space which generate H and CD dual. So if we ignore K, which is central element, takes the linear function of the remaining part, we will have this. And this space is R-dimensional space is invariant because if we take reflection of the root, it will be expressed through other roots. So this is more or less obvious. Another way is the following. We can take we can this this are plus one dimension. Another way I will another way is to take a quotient. We can take the space which is generated by alpha 1, alpha r, delta by 0. It takes the quotient of the space generated by delta. Actually, most standard way is to do this in a bit different way. So take the affine subspace here. Affine subspace, so the vectors of the form pi 0 plus some, say, xi alpha I plus, okay, where I goes from 0 to r, so such affine subspace. It's affine because the coefficient near pi 0 is equal to 1. And then they take quotient of the space by delta. This space is preserved by the space is preserved by the affine group because action of the affine group just adds roots, so don't change this coordinate. And then we can take quotient. I don't know, maybe some explanation. So we have one invariant one-dimensional space, and then we take hyperplane which is orthogonal to this one-dimensional space. This is. And since this one-dimensional space is invariant, then orthogonal complement is also invariant. But this picture is a bit misleading because this delta is a time-like, it has 0 norm. So it belongs to it is parallel to this affine space, so we can take the quotient. And we get R-dimensional representation, but so this will be R-dimensional affine representation. And the word affine, what is its origin? It is because one can say that this is because we start from the affine plane. And another explanation is that if we take reflection with respect to certain plane, which in the original space, which R plus 2 dimension, goes through origin, then it intersects this affine plane through some hyperplane, some subspace of one less dimension, but which is not, which don't belong to any origin, or which don't go through the origin. So we have some set of affine lines. So reflection with respect to this hyperplane will be reflection with respect to some affine line here. Affine subspace, not linear subspace, but affine subspace. Okay, who is still here? Who can, I don't know, ask something or complain about some or say something? Who is still listening?
Sorry, I'm very I don't understand what the affine representations. I'm not understand. Sorry, can you explain again?
By word affine representation, it means that this homomorphism not to the space of linear transformation of the space, but to the set of the affine transformation of the space. So this transformation do not preserve the origin.
So it's pi 0 is affine. It's mean.
No, so the representation B is affine.
Oh, okay, okay. Thank you.
I will give you an example of SL2 in a minute, but maybe somebody can ask even at this point. Okay, if nobody wants to ask, yes. Where's symmetry? No, no. Mij are given by some formula, and you will see an example. Yes, Mij is given by the formula on the blackboard. Sorry for people in the Zoom. Okay, let's take an example. Okay, example will be my favorite example. G is equal to SL2. Then, okay, I have not many ways, but anyway, let me, okay, I have to write down A and B, but let me first write down A, but on the bottom part, because I don't have space, and then write down B. So for A, I draw again the figure for the roots. And here is some, this, let's take this to be a carton. Then this alpha 1, which is equal to theta in this case. This is alpha 0. This is delta, which correspond to imaginary root. And all other roots are alpha 1 plus delta, alpha 1, alpha plus delta, alpha plus 2 deltas, and so on. And negative roots, here's the minus alpha, here's the alpha 0, which is minus alpha plus delta. Okay, let me move this picture a bit to the right. Minus alpha plus 2 delta, and so on. This is 2 delta, minus delta. Okay, so so we have, so how to see, what's drawn here? We have two-dimensional space. R is equal to 1. This is a two-dimensional space which is generated by alpha 0 and alpha 1. Or equivalent can be generated by alpha 1 and delta. By alpha and delta. Alpha 1. And the scalar products of them given by, as I wrote before, delta is 0 and alpha with itself is 2. Then what happens if I take any reflection? So for example, I can take reflection S1. Then S1 of alpha 1, which is the same as alpha, it will be minus alpha. Maybe I drew it like this. So S1, it maps alpha 1 to minus alpha 1. And what happens with alpha 0? Alpha 0 is minus alpha plus delta. If I take reflection S1, then minus alpha becomes alpha. And delta keeps the same. So alpha 0 goes to this element. And this element is the alpha 1, is alpha 0 plus 2 alpha 1. Get alpha 0 plus 2 alpha 1. Oh, it is equivalent to alpha plus delta. And this is minus. So in this picture, we have these two simple roots, and they go to this set of simple roots. This linear transformation, it preserves our form, but this is how it acts. And let me compute also S0. What happens to alpha 1 and alpha 0? Alpha 0 should go to minus alpha 0. And what happens to alpha 1? Okay, let us write down this explicitly. S0 of alpha 1 is equal to alpha 1 minus scalar product of scalar product of alpha 0, alpha 1. I do not write denominator, don't write 2 because all roots have length 2 times alpha 0. This is equal to alpha 1. Scalar product between alpha 0 and alpha 1 is minus 2, as you remember from Cartan matrix. So it will be plus 2 alpha 0. In terms of the generators alpha and delta, this is alpha, this is 2 delta minus alpha, yes. Okay, so I think yes, I think this is correct. So 2 delta minus alpha, or in terms of alpha 1 and alpha 2, this is 2 alpha 0 plus alpha 1. So we get some non-trivial linear transformations. If you want, so you can even, this formula can be drawn as some matrices. One of them is 0, minus 1, 0, 2. And this is matrix 1, 2, minus 2, 0. No, okay, everything is wrong. Okay, these two matrices. So each of these matrices is a reflection, as one can easily see, and they generate affine action of the affine wire group on this space. Are there any questions? If no, let's return to the representation B. For B, what do we have? We have, okay, still some time. For B, we will have, in this case, one-dimensional representation. It is a, okay, let me, how to write down this? So it is the space, the space is the elements of the form omega 0 plus some x alpha. And it could be also some delta, but we ignore delta. If we act by S1 on this space, then alpha 1 is orthogonal to omega 0 and invert alpha. So it will be omega 0 minus x alpha. Okay, now let's x by a 0. Maybe I should write down this more explicitly. So this is here plus c delta. So this element of the quotient, take the quotient by delta. Okay, now let's x by a0. Will be pi 0. Pi 0 plus x alpha minus scalar product as 0, let me call it delta minus alpha. Scalar product of delta minus alpha with pi 0 plus x will be 1 minus x, because delta has unit scalar product with pi 0. So we should substitute y minus x delta minus alpha. Plus c delta. So this is equal to pi 0 plus 2x minus 1 alpha if it is correct, of course. Let me check this. We should substitute alpha 0 with coefficient, which is a scalar product. So here before, maybe I should have lost 2. So I don't believe. This scalar product is, I think, 1 minus 2x. Here should be 1. Yes, this is more, makes more sense to me. And then we get minus 1 plus x alpha plus c. Okay, one more attempt. X minus 1 alpha plus c delta. Okay, I'm not sure that is anybody still looking with some care to this computation. Maybe it's easy to everybody to do this computation himself. But I want to, to finish this computation with some, I don't know, some sort of result. So result is the following. So we have a line, we have one-dimensional space with coordinate x on it. And S1 is a reflection with respect to this line. This is 1. So you see it maps x to minus x. And S0 maps x to minus x plus 1. So this is again a reflection with respect to point okay, I'll draw it here. 0 with respect to point 1/2. So point 1/2 is fixed. And this is this is again, we see that this is a fine transformation. So we have two maps. So one map is x to minus x. We have coordinate x, and another map is x to 1 minus x. And these two reflections generate the whole affine while group. This is why it's called affine. And for example, one can ask a question which I was asked in the audience some time ago: what is the meaning of the MIJs? For example, in this case. So we have reflections as 0 and as 1, and what will be the composition? As 0 and then as 1. It is well known that if you take two reflections, then the composition, it will be translation. So for example, in this case, this element has infinite order. In other words, in this case, the corresponding M01 is equal to infinity. In this, for such special metrics, for SL2 case, we do not have braid relation at all. The element has S0, S1 has infinite order. So this braid relation is in equivalent manner can be written as Si is j in power Mij is equal to E. For using the fact that all S is any S is inversion. And since in this case S0 S1 has infinite order, this translation, so we don't have braid relation at all. Okay, let me summarize what we get here. So representation, this calculation is representation B, which we constructed, given by reflections in H, in the space H star. And the reflections are given by the hyperplanes are given by the equation that alpha scalar product alpha and x are equal to n. This hyperplane H alpha n. And this actually for simple laced case. For non-simple laced, I have to put here H alpha check. So these are my affine hyperplanes. Let me draw, or maybe even not draw, but actually I prepared the picture for something which we will not come today, but so Okay, this is a picture for SL3 or A2 case. Here I draw all, maybe we don't need simple roots here, but everything else is okay. So here I draw all the affine hyperplanes under which we take a reflection. So this is a SL3 version of this picture. Here we have just sequence of the affine hyperplanes, and here we have this sequence. If we take, so I denote the reflection with respect to H alpha n by S alpha n. Corresponding reflection. Then if I take the composition of S alpha 0 and S alpha 1, this is T alpha, this is a translation. So if I take composition of two of the reflection with respect to parallel hyperplanes, then the result I get a translation. And from this picture, one can easily see the following formula: that affine while group is isomorphic to semi-direct product of the finite while group times root lattice.
The root lattice of the semi-simple Lie algebra, right? Not of the affine.
Root lattice of semi-simple Lie algebras, yes. There is some issue. One can take either original root H or H dual. In other words, root system phi or dual root system. This is important for not simple laced case. But while group are isomorphic, so actually you can take any of them. Original, no, this space is the original. The space is generated by original roots, not of the affine counterpart in this picture is not extra dimension, but another way we have more reflections. We can move the reflection line. So this W, which is not affine, this W is a while group of phi. So in other words, this is subgroup of WA, which preserves origin. So in this case, here I draw all the reflections, and this is a group generated by reflections which correspond to n equals 0. Another way, W is generated by S alpha 0. And this Q, I will improve my slides and then before sending them, putting them on the website. And that's some problems, but here just because I'm more or less have to stop now, so I just draw somehow in hurry. So Q is a root lattice, and Q is generated by T alpha, where T alpha are roots. Okay, so I plan to finish more or less in time, so I just say that, okay, maybe you can see that I have 17 slides. We are on the slide number 9. So it means that next time I will continue to talk about affine Lie algebra. It's okay. So what can we do? We have a big part, but I don't want to talk about affine while group. So I say that two things which I put in the slides and supply with problems, but do not plan to talk next time. So there is an extension of the affine while group. So there is a group I, which can be defined as W symmetry product with P, where P is now a root lattice. The P is a weight lattice. So here in this picture, you see we have translation with respect to roots, but roots are somehow larger than the root lattice is larger than weight lattice. So we can add. Okay, maybe this is not the good picture. So there are more translation. We can add more translation which preserves this picture. And this is affine, and this one more notion. And one more notion is a affine braid group, which is which we will use since, as maybe you remember from the last time, there is a braid group action of the quantum group, elliptic braid group action. So we have to know something about this braid group in the affine setting. And the affine braid group, it will be just the group generated by GIs T0, T1, TR, subject of braid relations. So without imposing that each S is inversion, is involution. And this group has some properties which I put in the slides and in the problems. But I don't want to go over time, so I stop here. Are there any questions about what I have said?
What is y to the power of lambda?
I will define in the slides. This is analog of the translation in the braid group. I will put slides on the side tomorrow, and if please look, and if you have questions about the subject, then ask me next time, or via email or any other. Okay, let me stop the YouTube